All right, so now we're going to mess with our understanding of time. And so in relativistic mechanics, as it turns out, there's no absolute length nor absolute time intervals. In this video, we're going to focus on relativity of time and time dilation, and in the next video, we'll look at relativity of length. But this is a very different way of thinking about time and length, and we're going to see that our understanding of time is fairly limited, as it turns out. Um, so in relativistic mechanics, if you look at events uh, that are happening at different locations and observed to happen simultaneously in one frame, what you may see is that in a different frame, they are not observed necessarily to be happening simultaneously. Okay, so we're going to see how we can figure out how the time intervals are going to be different. And to do so, we're going to look at an example, and we're going to build what we are going to call a light clock. And so this is our light clock, and to start, we're going to consider our light clock at rest. Okay, so this is similar to how we would measure the speed of sound, for example. We have a source, we have a detector, and so the light is emitted from the source. It's going to travel here, bounce back, and then be detected here. If we want to know how much time that took, we look at the distance traveled and we divide by the speed. So if the distance here is d, that means that the total distance traveled is equal to 2d. We divide by c, and that is the amount of time between the time that the light was emitted and when it was detected over here. And so this would be for our light clock at rest. So what happens now if our clock starts moving? So we're going to have now our clock moving at a speed v, all right? It's constant, so that we can consider this to be an inertial frame of reference. And so you can see that there's going to be a difference here, because now if we compare the distances traveled, when before we had 2D, now we're going to have to travel further, all right, between the time of emission and the time of detection. All right, so we're going to solve and figure out how much time now we have between the two events, when the light is emitted and when it is detected. Okay. All right, so since the clock is moving at a speed v, then we know that the distance traveled between here and here in an amount of time delta t, which is the time that we're measuring, that's going to be v delta t. Okay, d is still the same distance, that has not changed. And if we look at here, the distance traveled during that time delta t. So technically we would have traveled all of this. So if we look at half of the motion over here, we have traveled the distance, which would be the speed times the time interval. So if it's half of it, it's the speed times delta t divided by 2. Okay. And so we're going to use the fact that with this example, we have a nice right triangle, so we can use Pythagorean theorem. So if I call this side A and the side B and the side C, we can write that a squared equals b squared plus c squared. Okay, so if I apply this to this particular example, then I would write that c squared times delta t over 2 squared is equal to then b squared, which is d, so d squared, plus this part, which is half of the whole motion. So again, we're going to have something looking similar. So v squared delta t over 2. Whoops. Okay. All right. And now the whole point is to figure out what this delta t is. So I'm going to simplify. I'm going to bring this on the other side, and that means that I'm going to end up with c squared minus v squared. We'll say that's divided by 2 squared, so 4. If you want to skip the details of this calculation, you have the results at the bottom. So this is times our delta t squared equal to d squared, and you can see that that means that delta t squared is equal to 4 d. It's very hard to write with this thing. And then I have to divide by c squared minus v squared. Okay, so all that to say that we can actually express delta t here in terms of d, which is the distance that we have between the source of the detectors and where the light is bouncing off, and then the square root of c squared, where again c is the speed of light, v here is the speed of the frame. So now that we have this clock that is moving at a speed v, so we can compare that. So if we compare that to what we had before we had just 2d over c. Okay, so we can actually rearrange this so we can see the 2d over c, and what we end up with is a formula that is the general formula for time dilation, which tells us that delta t, so this is in the moving frame of reference, is the delta t in the frame that was at rest divided by square root of 1 minus v squared over c squared. Okay, so that's interesting because, as you can see, we measure a different time interval. This number we saw according to the second postulate is less than 1 because we know the speed of our frame of initial frame of reference is less than c. So this is less than 1, 1 minus something that's less than 1 but more than 0 gives us a number less than 1. So we're dividing by something that's less than 1. And so that means that if we compare, the moving clock actually appears to run slower because the delta t that we measure is greater, the time interval is greater. So as it turns out, you can apply this to any other frame of reference. We can apply that to any other system. One thing that I would like to point out is that we call this time dilation because you can see that here we're divided by, again, a number that's less than 1, so we end up with a delta t that is greater. So and you may start saying, so why is it that we've never actually included this in any of the thing that we've done before? Because we had frames of references that were frames of reference that were moving with respect to each other. One thing that you can see is that this effect is going, so if v is very small compared to the speed of light, this effect is going to be very small. So it's only going to be noticeable for what we call relativistic objects. So that means that when v starts getting closer to c, then it's an actual fraction of c, then it's noticeable. But if you're not moving fast enough, you're not going to, the effect is there, it's just negligible, okay? And we can see that if we look at here, the ratio of the times in the time intervals with respect to this, how fast you're going, right? So you can see that those delta t and delta t naught, they're almost the same. You know, for a while you can't really see the difference. Once you start moving very fast, especially if you're really close to the speed of light, then you will see a difference. Okay, so we're gonna have to use some definitions here because now our definition of time is going to be a little bit different, right? So What we're going to call an event is a physical occurrence that happens at a specified location at a specified time. So that's what we're going to call an event. And what we're going to define to be the proper time is the amount of time separating two events that occur at the same location. Okay, so for as an example, the proper time between ticks in a light clock is the time between the emission of light and the detection. So those were the two events when the clock is at rest relative to the observer. All right, and so that is how we define the proper time, and that's how we define the events. So is that something we actually measure, and is it just something that that's Einstein's come up with? So time dilation has actually been measured, and so on some atomic clocks, and it's also something that is used a lot in particle physics experiments. So if you look at subatomic particles, they are moving at speeds that are close to the speed of light, and you can see that, especially when you look at the lifetimes of such things. What is also interesting is that time dilation makes it so that different observers will disagree about the simultaneity of events occurring at different places. And we're going to talk a little bit more about that, and we'll talk about what we call the twin paradox in a second. But before then, I just want to go over an application of what we just saw. And we're going to be looking at muons. We're going to look at high energy particles that come from space, and they interact with atoms in the atmosphere. Never mind. So the muons are the result of the interactions of high energy subatomic particles that interact in the atmosphere. And the muon decays with a mean lifetime of 2.2 times 10 to the negative 6 seconds, as measured in the frame of reference in which it is at rest. Okay, so if a muon is moving at, you can see a very high speed, so 99% of the speed of light relative to the Earth. If you are watching from Earth, what are you going to measure as the lifetime of the muon? So we're going to apply, so I would pause if you want to do this without looking at the solution first. And just to get an idea of how significant this is, okay? So, and in this case, you can see that when we looked at the graph, when we were at speeds that were close to the speed of light, we actually, the curve blew up, right? So this is something where we should see a very large effect. So let's see how that works. So according to what we saw, delta t, and that is in the moving frame. So that's what we're trying to measure here is going to be delta t naught. Okay, so that is in the measured in the frame of reference where it's at rest, divided by the square root of 1 minus v squared over c squared. So okay. So this number here is given by the mean lifetime in the frame of reference when it's at rest. So that's our 2.20 times 10 to the negative 6 seconds divided by the square root of 1 minus. So here this would be, the v is the speed of the in the so relative to the Earth, right? So we saw that this 0.99 times c. Okay, so in this case, so because we're on the Earth and the muon is moving at 0.99 c relative to the Earth. Okay, so that's the speed relative of the the inertial frame of reference where we're sitting, where we are doing the observation. So 0.990 times c squared divided by c squared. So you can see that the c's are going to actually go away. So we take our calculators and we're going to measure 2.2 times 10 to the negative 6, which as you can see is actually very short, right? And we're going to divide that by the square root of 1 minus 0.99 squared. All right, so this gives me 1.56 times 10 to the negative 5 seconds. So you can see that we see a very large difference because we were at, so this would be, if you want to compare, 15.6 times 10 to the negative 6 seconds. So you can see that it actually did change the ratio quite a bit. All right. So that is interesting because it's something that you can, if you have something that is moving very fast with respect to the frame of reference, you're going to see a large effect due to this time dilation. Okay. And that also will give you if you want to know, how much distance the muon will travel in the atmosphere, then you would take this time, so 15.6 times 10 to negative 6 seconds, and you will multiply by its speed, so 0.99 times c to figure out, and it's a few thousand meters. And again, that's because we're looking at it when it's not in a frame of reference where it's at rest. Okay, it's moving actually really fast. One more thing, because as you might be a little bit or very confused by these ideas, and it makes sense. And it's because it's really far from what we experience, what we've seen so far. And so there is this paradox, which is called the twin paradox, that states, okay, so this is very confusing. So are you telling me that if we take two identical twins, and so they're going to be astronauts, we're going to call them astronaut A and astronaut B. All right, so astronaut A is going to stay on Earth while the twin, astronaut B, is going to take off on a high-speed trip through the galaxy. All right, so due to time dilation, to astronaut A, astronaut B is going to age more slowly. So when astronaut B returns to Earth, it's going to be younger than astronaut A. So the paradox is that, can astronaut B make exactly the same arguments to conclude that astronaut A is in fact younger, right? Because the astronaut B is moving with respect to astronaut A with the same relative speed. So each twin would measure the other one to be younger. So that's the paradox. So how does that work, and how is it something that is even possible? Beyond the fact that we would be moving through the galaxy at high speeds. All right, so this is where you have to remember the postulates, because it turns out that everything makes sense if you remember that we said that we have to look at frames of reference that are inertial, which means that they are not accelerating. So if astronaut B moves and returns back to the Earth, there has to be an acceleration there, all right, in order to return to the Earth. So that's not a frame of reference that is inertial. So astronaut A is correct because astronaut A was the one that stayed at rest, that was not accelerating. And so when astronaut B returns, he would be younger than astronaut A. All right. So next, we're going to now make length confusing. Now that we talked about relativity of time, we're going to talk about relativity of length, and you can see a little bit where this is going, because we saw that, so if the time intervals are going to change, that means that our lengths are also going to change. And we're going to see how that works in the next video. All right, thanks. Bye.